Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. In the previous episode, we covered some of the principal motivations for studying thermodynamics in chemical engineering. We also covered its principal goal, which is to understand and predict how groups of molecules will behave at equilibrium. This goal is predicated on the idea that we have a meaningful way to describe and measure aggregate behavior of groups of molecules. That brings us to today's topic, which is to discuss in a bit more detail what aggregate behavior really means and how workers describe it, including the concept of a thermodynamic state and the terminology and variables used to describe it. In order to frame the task before us, I'd like to share with you another one of my favorite thermo-themed cartoons. A classroom full of students is patiently waiting for the arrival of their teacher, apparently ignoring the prominent announcement on the blackboard stating, in English, that their English as a second language class has been canceled. This cartoon highlights what I think is actually an easily overlooked catch-22 aspect of learning thermodynamics, which is to understand the language of thermodynamics itself. It's probably self-evident that we need to cover some terminology before we can explore the foundations of thermodynamic theory. However, my experience as a student and later as an educator is that when you really break down the underlying scientific principles of thermodynamics, they are deceptively simple. Mass and energy are conserved. If a group of molecules are constrained in some way, releasing that constraint will result in more ways for them to rearrange. And yet, hidden in these obvious statements lurk a host of less obvious consequences and relationships that are nearly impossible to recognize without some fluency with the language and framework used by scientists and engineers to describe equilibrium behavior. I think most of the intellectual challenge of understanding thermodynamics is actually developing this fluency. So my goal with this episode is to introduce some of the principal elements of this language and framework. One of the first elements of this framework we should discuss is the concept of a system. Before we can describe the aggregate properties of a group of molecules, we need to first specify which molecules we're talking about. Although at first glance this might seem obvious, in practice, some of the most confusing issues in thermodynamics arise from ambiguity about which molecules are under consideration, especially when the molecules are transforming, changing phase, moving around, and entering or exiting a region of space. To keep from getting confused, workers have developed a formalism and nomenclature to help distinguish the specific group of molecules under consideration from the rest of the world. This group of molecules is usually called the system. The system occupies a region of physical space called the control volume, which is surrounded by an imaginary boundary separating these molecules from other molecules or regions of space. Within this system, we ascribe physical properties to the molecules. The space outside the boundary is called the surroundings. Unlike the system, we usually don't ascribe any specific properties to the surroundings, although in some cases we do define the values of some system properties, such as temperature or pressure, at the boundary. Taken together, the system plus surroundings are usually called the universe. This is not the universe we usually think of as in astronomy. In thermodynamics, the universe is more of a theoretical concept, a very large region of space that obeys certain constraints, such as mass and energy conservation. Although in some cases the system boundary corresponds to a physical boundary of some kind, like a container wall, this is not a requirement. In fact, in most cases the boundary is really an imaginary construct used to identify the molecules we care about and provide a specific control volume for applying conservation laws, such as mass or molar balances or different types of energy balances. To that end, workers further classify systems into three different types according to the flow of mass and or energy across the system boundary. The first is an isolated system, defined as a system that does not exchange any matter or energy with the surroundings. One corollary characteristic of an isolated system is that it is usually of fixed volume. This is because any change of system volume generally requires doing work on the molecules inside, which would violate our original constraint that no energy exchange occur. For this reason, isolated systems are often idealized as a perfectly insulated, rigid container containing the molecules. A second type of system workers often distinguish is a closed system, defined as a system that exchanges energy with the surroundings, but not matter. A closed system is often idealized as a piston cylinder assembly that allows thermal energy to flow in or out through the cylinder wall. This flow of thermal energy is called heat. The assembly also allows the flow of mechanical energy into or out of the system via compression or expansion of the piston. Such a flow of mechanical energy is called pressure volume work, PV work, or sometimes just work, depending on the context. Other forms of energy transfer into or out of a closed system are also possible. However, PV work is the most common one we need to consider because it is associated with most changes in molecular aggregation, something we'll discuss more about later. Note that with this nomenclature, heat and work are not forms of energy contained by the system or surroundings, like kinetic energy or potential energy. In fact, heat and work are not properties of the system or surroundings at all. The term heat and work refers to the manner in which energy flows across the system boundary. Why would the way the energy flows make any difference? Well, as we'll see later, the distinction between heat and work is really that they involve different constraints on how the molecules can rearrange themselves in response to changes in energy content. Finally, a third important type of system is an open system, defined as a system that it can exchange both matter and energy with the surroundings. Although this is the most general type of system, open systems are usually applied with other constraints. For example, they're often used for understanding groups of flowing molecules entering and exiting a fixed volume at steady state. You might recall using open systems in Chemie 310 to formulate mass and energy balances for purposes of analyzing steady-state processes. In thermodynamics, open systems are often used to analyze continuous energy conversion and in analysis of process efficiency. Okay, so now that we have specified which group of molecules we're talking about, the system, how do we go about describing the aggregate behavior of molecules inside the system? This brings us to a second key element of our theoretical framework, an idea known as the continuum approximation. In brief, the continuum approximation basically says that when our system contains a very large number of molecules, we can meaningfully describe their behavior in terms of predefined and measurable thermodynamic properties, such as temperature or pressure, rather than calculating these properties as an average from the states of individual molecules. To help illustrate why the continuum approximation is valid and so useful, consider the following example. Imagine you're an astronaut living and working on the International Space Station in zero gravity. You prepare a small amount of boiling water and put it inside a rigid thermos that originally contained a vacuum. In the absence of gravity, the water drifts around, but eventually mostly coalesces into a single floating mass. Meanwhile, some of the water evaporates, filling the remaining volume of the container with steam. This evaporation causes the remaining mass of water to cool off a bit. Eventually, the system reaches equilibrium. At this point, we'd like to meaningfully describe and quantify the properties of the H2O molecules inside the container. To begin, what type of system is this? Well, if we draw our control volume around the H2O molecules and assume the walls of the thermos are perfectly rigid and insulating, this would be an example of an isolated system. Because the system is isolated, the total amount of H2O cannot change, nor can its total volume or energy content. Our goal here is to understand what the molecules will do at equilibrium under these constraints. To gain some insight, let's take a look at a computer simulation of a two-dimensional Lennard-Jones fluid, a commonly used molecular model for the behavior of liquids and gases. As we'll explore in a few weeks, the physical laws assumed in this model are amazingly simple. All we're doing here is solving Newton's laws of motion, force equals mass times acceleration, for each molecule, as if it were a spherical ball traveling through two-dimensional space, colliding with each other and the walls of the container. The only extra rule is that the molecules, like water, are attracted to each other by a short-range force. We also keep the number of molecules and total energy of the system fixed, so that the molecules in our simulation experience the constraints of an isolated system. As you can see, the atoms spontaneously form a similar arrangement as we expect for the H2O in our thermos. We see a drifting blob of liquid-like substance surrounded by a gas-like substance. But what's happening at the molecular level? It looks like total pandemonium. Molecules flying around randomly, banging into each other, banging into the walls of the container. The molecules in the liquid are rattling around, unable to break free, till they get to the surface of the droplet and then get ejected into the gas. Meanwhile, gas molecules constantly strike the surface of the droplet, most of them bouncing off, but many getting trapped and ultimately condensing. Even though the volume, mass, and energy are constant, at the size scale we are simulating here, the system is rapidly and constantly evolving from one molecular configuration to another, to another, to another, never really calming down. And yet, if we carefully measure all these molecular level fluctuations and start to calculate averages, we start to get a different picture. Consider the temperature, which you might recall from first-year chemistry is closely associated with the average translational kinetic energy of molecules. The kinetic energy of a molecule is proportional to its mass times the square of its speed. In this simulation, the speed of each molecule is indicated by its color. Based on this, we can see that after reaching equilibrium, the speed, and thus the kinetic energy of the molecules, is, on average, rather similar throughout the container, including molecules in both the liquid and gas-like regions. In order to quantify the temperature, we can calculate the kinetic energy of each molecule, sum over the molecules, and then divide by the number of molecules to get the average. We can then average this value over time to calculate a quote-unquote temperature, reported here. What we can see is that over time, this average stops changing. In other words, temperature becomes a constant and spatially uniform property that describes the kinetic behavior of the molecules as a group under this set of conditions. As another example, consider the pressure inside the simulation box. The walls of the container mostly see a vacuum which has no pressure. However, you might recall from classical physics that each time an object strikes a surface, it imparts a momentum impulse given by the object's mass times the change in velocity perpendicular to that surface. If we add up these momentum impulses over time and divide by the time we were counting, we get a force. If we divide that force by the area of the wall over which the collisions occurred, we get a pressure. At a molecular level, that's all pressure really is. And if we take this average long enough, as reported here, we again see that at some point, this average stops changing with time. We also might expect that because the molecules spread out randomly in all directions, the pressure is uniform on all surfaces. Indeed, when the system is at equilibrium, any hypothetical surface we insert into the system must have a balance of molecules crossing it in both directions, implying the pressure must eventually become uniform everywhere. As such, pressure becomes a meaningful property describing the momentum transfer properties of the molecules as a group against imposed surfaces. Finally, we also see that over long periods of time, the rate of evaporation of molecules from the liquid droplet to the gas and the rate of condensation of molecules from the gas to the liquid become balanced, such that the relative quantities of liquid and gas also do not change with time. The simulation doesn't force that to happen. The molecules just do this naturally as a result of reaching thermal and mechanical equilibrium with fixed energy content. As we'll discuss, this is an example of phase equilibrium, where more than one stable arrangement of molecules can coexist at the same temperature and pressure in a dynamic state of equilibrium. Returning to our thermos of H2O, we might expect a similar situation to prevail. However, unlike the Lennard-Jones model, which only has 1,000 molecules in it, our H2O is macroscopic. For example, let's say our thermos contains 300 grams of H2O. Dividing by the molecular weight, and then multiplying by Avogadro's number, this gives us about 10 to the 25th molecules. For macroscopic groups of molecules like this, molecular averaging occurs so quickly and on such a tiny length scale that we can't see it. We just see something like this: a quiescent, spatially homogeneous liquid with macroscopically measurable characteristics such as temperature, density, vapor pressure of steam around it, surface tension, etc. In fact, the number of molecules is so overwhelmingly large that we can describe local spatial variation of these properties from place to place over distances of microns, as if these properties varied continuously in space. Hence the term continuum approximation. It's not that these properties are unrelated to molecular behavior. They are directly related, as we saw in the simulation. But we don't have to measure and describe what every individual molecule is doing in order to define, measure, and theorize relationships among these properties. Indeed, the scientists who first began developing thermodynamic theory didn't have computers, and in some cases their work predated atomic theory itself. Yet they were still able to lay much of the foundation for understanding relationships among properties arising from molecular behavior. This is the beauty of the continuum approximation, and why it has been and continues to be such a cornerstone of thermodynamic theory. A closely related idea that stems from the continuum approximation is the concept of a thermodynamic state property. What we observed in our discussion of zero-gravity water is that the macroscopically observed average behavior of the system could be uniquely and adequately described by a relatively small list of properties, such as the volume, number of molecules, energy content, temperature, pressure, and quality Q, defined as the fraction of molecules occupying the gas versus the liquid. In thermodynamics, we call these types of variables state properties. Thermodynamic state properties possess a number of useful characteristics. One of the most important, which is shared by all state properties, is that they are path independent. This means that their value does not depend on the route the molecules took to arrive at their current state of aggregation within the system. This is because molecules don't have a memory, so what they do at equilibrium can't depend on what happened to them before they got to a particular state of equilibrium. In thermodynamics, we often define other variables, like heat and work, that are path-dependent. These variables sometimes represent averages over many molecules, so may also obey the continuum approximation like state properties. However, they don't describe the state of the molecules at a given moment. They describe a pathway or constraint imposed on the molecules while transforming from one state to another. An apt analogy is altitude versus travel distance. Imagine you're climbing Mount Rainier. On summit day, you wake up at 1 a.m. and climb from Emmons Flat, altitude 9,800 feet, to the Columbia Crest, altitude 14,410 feet, for a total change in altitude of 4,610 feet. Your planned route is to follow the Emmons Glacier to Disappointment Cleaver, ascending the southeast side of the caldera. However, due to rockfall in the Ingram, you decide instead to swing north toward Liberty Cap and ascend the northwest ridge. This improvised route ends up taking you nearly a half mile out of your way, adding significant time and effort required to make the climb. However, the ups and downs of your new route still add up to 4,610 feet, exactly the same total change in altitude as your original plan. In this analogy, altitude is a state property. It's a characteristic of the beginning and ending states of the climb and can be calculated without specifying the route at all. In contrast, travel distance, time, effort, injuries, hypothermia, etc. are all properties of the path you took to get from the beginning to the ending state. As we'll see, this distinction is critical to understanding and quantifying the energy and entropy content of molecular systems. Another important characteristic of state properties is that they can be intensive or extensive. For example, imagine our system is the water in this partially filled glass at 1 atmosphere and 20 degrees C. We now double the amount of water by combining it with another identical glass having the same thermodynamic state as the first glass, extending the system boundary to incorporate the larger mass of water. What properties of the system have changed? A number of properties we can think of will have doubled: the mass and number of moles of H2O, the volume, the energy possessed by the water, the number of moles of any mineral solutes, the entropy of the system. These are all examples of extensive properties. Variables used to express extensive properties, also known as extensive variables, scale linearly with the amount of material in the system. In thermodynamic theory, extensive properties serve a particularly important role because they often appear in conservation equations, such as mass and energy balances, or other accounting relationships. In contrast, we can also think of a number of properties that will not change by doubling the amount of water, provided the water in the two half-filled glasses prior to mixing is identical. These include temperature, pressure, density, and the mole fraction of any solutes in the water. These are all examples of intensive properties. Variables used to express intensive properties, also known as intensive variables, are independent of the amount of material in the system. The significance of an intensive property in thermodynamics is that it often reflects the way that molecules are arranged within the system. Two particularly important intensive properties that we usually consider are temperature and pressure. As we saw in the computer simulation of a Leonard-Jones fluid, temperature and pressure become spatially uniform within fluids as a consequence and condition of reaching thermal and mechanical equilibrium, even when other intensive variables, such as density, are not spatially uniform. As we'll see shortly, a system can contain multiple groups of aggregated molecules, or phases, like a liquid and a gas, which share the same temperature and pressure, but which differ locally in other intensive properties, like density, concentration, and so forth. A large number of intensive properties we can think of are actually a ratio of two extensive properties. For example, the density of a system is defined as the mass of that system divided by the volume of that system. Mass and volume are both extensive, so if we double the size of the system, they both become twice as large. But this factor of 2 cancels when we take the ratio in the density. In chemical engineering, we often work with molar properties, defined as an extensive property of that system divided by the number of moles. In my notes here, as well as in your textbook, molar properties are often distinguished from their extensive counterparts by using a lowercase letter. For example, molar volume is the volume divided by the number of moles. Molar entropy is the extensive entropy divided by the number of moles, and so forth. Likewise, we can also define a similar family of mass-specific properties, defined as the ratio of an extensive property of that system to the mass of the system. In your textbook, mass-specific properties are often symbolized as a lowercase letter with a caret over the top of it. An additional distinction that I think is useful to draw is between phase-intensive and system-intensive properties. If we draw our control volume such that our system only contains one uniform aggregation of molecules, called a phase, any molar or mass-specific property we define is a meaningful characteristic of the local aggregation of the molecules. For example, consider a system of fixed volume containing salty water. The salt concentration and density that we calculate based on the extensive masses of H2O and salt in the system is also a valid local description of any subgroup of the molecules, such as 2 different liquid samples taken out of the glass, provided these samples are large enough to still obey the continuum approximation. If we change the overall concentration of salt in the system, as illustrated by this series of photos, this change will be felt uniformly everywhere within the liquid as a shift in local concentration and local density. Intensive properties that are directly linked like this to the local composition and structure of a phase, I like to call phase-intensive properties. However, what happens if we have more than one distinct phase in our system? For example, here is a glass of salt-saturated water, which has as much salt dissolved in it as possible at this temperature. Any additional salt we try to add remains undissolved at the bottom of the glass, even at equilibrium. If we define the boundary of our system to include both the salty water and the solid salt, and calculate the average density of the system, we find that it increases with the overall mass fraction of salt. However, the local density and salt concentration in the liquid phase itself remain fixed as more salt is added, because it's already saturated. Rather, the shift in the overall intensive properties of the system is caused by a change in the ratio of solid salt to salty water, while the phase-intensive properties of the solid salt and saturated liquid phase remain constant. In other words, changes in the intensive properties of the system as a whole are not associated with any local changes in molecular aggregation within the individual phases. Intensive properties of a system that depend like this on both the properties and relative amounts of various phases in the system I like to call system-intensive properties. If we know the densities of saturated salty water and solid salt, as well as the relative amounts of these phases in our system, we can calculate the average density of the two-phase mixture. Conceptually, this involves three steps. First, we need to express the density of the system, which is intensive, to the mass and volume of the system, which are both extensive. Once expressed in terms of extensive variables, we can employ conservation statements, in this case requiring the total mass and total volume of the system to be a sum of the masses and volumes of the two individual phases. Finally, we can relate the volume of the individual phases to their individual masses and densities. The resulting expression tells us that the reciprocal density of the system will vary linearly with the phase fraction, F sub s, of the system which is solid versus liquid. Shown here is a plot of the reciprocal density versus the phase fraction of solid. Note that the average reciprocal density of the system, which is system-intensive, varies with the phase fraction of solid, but the reciprocal density of the individual phases, which are phase-intensive, remain constant. If I had to point to one concept that confounds students of thermodynamics more than any other one, it's this one. Intensive versus extensive properties and how they scale with changes in overall system content and the states of individual phases inside the system. These ideas are central to the vocabulary and grammar of thermodynamics, to the point that it's almost impossible to understand the more scientific principles of thermodynamics without mastering them first. For this reason, we will be spending significant time over the next couple of weeks building this vocabulary and grammar.